So several people asked me over the last week, what does one do in the absence of spectral gap? And of course, this is the most important situation nowadays because the case of spectral gap is more or less understood. So what we're going to do today is we're going to talk about what can one say in the absence of spectral gap. So first of all, I would like to say that there are certainly dynamical situations of interest where there is no way to find an interesting Banach space on which a transfer operator acts with spectral gap. The reason for this is that as we saw over the last couple of lectures, spectral gap implies exponential decay of correlations, it implies central limit theorem for nice bounded functions, and so on and so forth. And there are dynamical situations when these things simply do not happen. So some obstructions for spectral gap. To spectral gap include slow decay of correlations. They include the breakdown of the central limit theorem. And more generally, something that was already mentioned in the talk of Juan Rivera Letelier, phase transitions. So for a typical example of a situation like this, consider the following map. This is probably the simplest example where something like this happens. You take the Manneville-Pomont map, a map which is expanding everywhere except an indifferent fixed point. So here you have an indifferent fixed point. So the Manneville-Pomont map, which is the map that people usually talk about, is T of x is x times 1 plus x plus 1 over s for s which is not too big. So this map exhibits slow decay of correlations, and by the end of this lecture I hope to show you a tool how to prove this. Now, it's not a coincidence that there is an indifferent fixed point which is responsible to the problems. Usually some form of non-uniform expanding or non-uniform hyperbolicity is related to obstructions to spectral gap. Now, there is a very general technique for handling situations such as this. So what one can do is one can correct the lack of hyperbolicity or the lack of uniform expansion by speeding up the iterations. So the simplest possible procedure is inducing, as it is known in ergodic theory, first return time inducing. So what you can do is you can use the following procedure. I will state this procedure in the general ergodic theoretic context because it actually holds it's applicable in quite great generality. So suppose x b mu t is a probability preserving transformation. And suppose A is a set of positive measures. Then it follows that by Poincaré recurrence theorem, it follows that the set A prime, which consists of all points in A which return to A infinitely many times, infinitely many n bigger than 0, this has full measure. Full measure in A. This is a result of the Poincaré recurrence theorem, which says that almost every point in A will return to A again and again and again. And then what you can do is you can define the first return time. So it's the first time after 0, when you return to A, and you define the induced map. Which is a map on A prime. Ti of x is equal to T phi of x of x. So what's this good for? Well, imagine for a minute what happens if we take this as our set A. Then when you calculate the derivative of T phi A, okay, this will be a product of derivatives, T prime T phi A minus 1x times T prime T phi A minus 2x, all the way up to T prime of x. But if you only consider points here, then this term is bounded away from 1, and all these terms are bigger than or equal to 1. So the product will be bounded away from 1. In other words, if you apply this procedure with this set A to this map, suddenly the problem coming from the indifferent fixed point goes away. And what you end up with is a uniformly expanding transformation. In fact, this transformation looks like this. So this is A and this is A. It will have infinitely many branches which have this form. And I don't know if this reminds you anything, but I hope that it reminds you the form of the Gauss map, because for all practical purposes it behaves in exactly the same way. And the same Banach space that gives you spectral gap for the Gauss map, namely the space of bounded Lipschitz continuous functions, will also give you spectral gap for the induced map for exactly the same reasons. So this situation, when you have a map which cannot possibly have a spectral gap because it has slow decay of correlations, but has an induced map whose transfer operator does have spectral gap, is actually very common. In fact, whenever you have a map with infinite Markov partition, if you're using a measure whose Jacobian is smooth, is let's say Hölder continuous, and you induce on one of the Markov elements, the result will be another map whose spectral gap will have, whose transfer operator will have spectral gap. Whenever you have countable Markov partitions, you can find sets A, in fact these are just the elements of the partition, for which this trick will work. Yes, whenever you have a map which has a countable Markov partition, and whenever you're dealing with a measure whose log Jacobian function is Hölder continuous, if you induce on a Markov rectangle, on a Markov element, the transfer operator of what you get will have spectral gap on some interesting Banach space. Yes? You have many possibilities for A. We'll get to that. We'll get to that. So, right, so I don't want to get into the details, but I'll just hand wave. When I talk about Hölder continuity, I talk about Hölder continuity with respect to the norm adapted to the partition. When you pass from the Markov partition of the Manneville-Pomont map, which is this one, to the Markov partition of the induced map, the rectangles of the Markov partition of the induced map are so tiny that although, as you say, minus log of the derivative is not Lipschitz with respect to the original Markov, the metric induced by the original Markov partition, it will be Lipschitz with respect to the metric induced by the new Markov partition. But I don't want to write the details. Okay, so the only thing that I wanted to say is that the technique of inducing does allow you to get over problems associated with the lack of uniform hyperbolicity. And the question arises whether one can use the spectral gap of the transfer operator for the induced map to obtain information on the transfer operator for the original map, which does not have spectral gap. Okay? So this is what I would like to talk about today. So the question is, I'll just state it again, because I said it a little bit quickly. It's just a technical question, yes? It's a technical question. How to use the spectral gap of the transfer operator of the induced map, okay, the induced map, to obtain information on the transfer operator of T, the original map, which does not have spectral gap possibly on anything. Okay? Do you understand the problem? So that's what I want to show you. Today there is a method for doing this. So this method is the following. It's called the operator renewal theory. Oops. And before I tell you exactly what this method is doing, I would like to start with a couple of identities related to transfer operators of maps and induced maps. So here are some identities. So the first identity is that the transfer operator of the induced map is given by the following formula. Actually, I don't want to write it like this. Its sum, n goes from 1 to infinity, t hat n, f restricted to the part of the space where the return time function equals n. There's nothing mysterious about this. I remind you that the transfer operator is the action of the dynamical system on densities. So what you do is you take a mass density on A, and you chop it according to how many times does it take the points to return to A. So if it takes a point n times to return to A, you move it n times. Okay, there's nothing particularly interesting about this. I would like to write it in a strange way, okay? If you don't mind, I would like to add here the indicator of A on the outside. This is really silly and unnecessary because if you have a piece of mass that returns to A after n times and you move it n times, then of course it will end up in A. So I don't really need to add this indicator. This function is always supported inside A, but I would like to do it anyway. Okay, so here is another identity. Let's look at the summand here, and let's give it a name. So let RNF be the summand. So it's this operator. So this is an operator on L1 of A. And let's make another definition. Let's call TNF the operator which is the usual transfer operator. So I take a density restricted to A, move the mass n times. Now some mass will not return to A. Okay? Some mass will return to A, some mass will go move some other places, so I multiply on the outside by the indicator of A. Okay? I define two operators, that's another operator on L1 of A. So the identity that I would like to write down is this. Tn equals Rn plus Rn minus 1 T1 plus Rn minus 2 T2 all the way up to R1 T n minus 1. And it's also true if you flip. It's also equal to Rn plus T1 composed with Rn minus 1 plus T2 composed with Rn minus 2 all the way up to Tn minus 1 composed with R1. This is called the renewal equation. It's called the renewal equation because a similar equation for numbers, not operators, appears in classical renewal theory. Okay? So, what's the excitement about the renewal equation? To understand why this may be useful, I would like to rewrite this equation in generating function form. And then I will explain to you how it can be used. So, let's introduce two generating functions, operator valued. Let T of Z denote the operator identity plus sigma n goes from 1 to infinity Zn Tn, and Rz be the sum n goes from 1 to infinity Zn Rn. So these are operators on L1 of A. And in order for things to work, I have to take a complex number less than 1 in absolute value. And then things will converge. They will converge because the norms of Rn and Tn as operators on L1 are less than or equal to 1, as you can verify. So now, how do these equations look in generating function form? They look like this. T of Z is identity minus R of Z inverse. How do you see this? You check. So you multiply TZ times identity minus RZ. This is a product of two power series. You open the brackets, you collect terms, and what you will find is that what multiplies the Z to the n is a convolution of coefficients from this power series and this power series. And these are exactly the convolutions, and the renewal equation tells you what this convolution is equal to. So you can just calculate and see that it's equal to the identity. And then you do again with the other direction. And you get this. Okay? So this is the renewal equation. Now, how are we going to use this? So here's the idea. The common thread in all that I've been telling you about during this week is that there is a lot of dynamical information encoded in the way that the iterates of the transfer operator converge to the limit. We deduced the Gauss-Kuzmin-Levy theorem and bounds on decay of correlations, and in a more sophisticated way, the central limit theorem from the analysis of this sequence of operators, t to the power n. Okay? Now, this function here, tz, is a generating function of t to the power n, at least when you act on functions supported inside A. So, tz contains information or is a generating function of t hat n f a. Well, if you apply it to a function f. It's a generating function of the iterates of the transfer operator on a function. So anything that you can say about this generating function and about its coefficients is going to be useful. It's going to be information on the way that the transfer operator converges to the equilibrium. Okay? So tz is the function that we want to understand. Except that we cannot because we don't have spectral gap. But now let's look on rz. Rz, at least when z is close to 1, is close to R1. R1, if you just follow the definitions, this is Rn, it's just the transfer operator of the induced map. So Rz is a perturbation of something with spectral gap. So this equation expresses the generating function of the iterates of the transfer operator, on which we don't know anything because we don't have spectral gap. It expresses it in terms of something else that does have spectral gap, a perturbation of an operator with spectral gap. Mind you, it's not an analytic perturbation. It's a singular perturbation, because if you look at what happens to the series sigma Zn Rn, this is 1. This is where you get the operator with spectral gap. As long as you move inside the disk, you are okay. But as soon as you move outside the disk, this series can fail to converge. So it's not an analytic perturbation. And that is why we will get new phenomena other than exponential decay of correlation, central limit theorem, and so on. It's because there are singular perturbations involved. So now, on the technical level, what we need to do is we need to be able to understand what is the effect of this operation, identity minus an operator with spectral gap inverse. What does it do to the asymptotic behavior of the coefficients? So this question for numbers is well understood. That's what renewal theory is about. Renewal theory is about the situation when Tn are numbers, Rn are positive numbers, and it tells you, subject to assumptions on the asymptotic of Rn, what happens to the asymptotic behavior of Tn. So we need to do exactly the same thing, but for operators instead of numbers. So let me state now the theorem that does this. So first, I will state it on an abstract level, not for transfer operator, but for general operators. And then we will specify to the dynamical context and see what it gives you dynamically. So here is the question. So here is the abstract setup. So L is a Banach space. And Tn are bounded linear operators such that Tz defined this way converges on the open unit disk. So in the notes I wrote closed unit disk, that's a typo. Should be the open unit disk. So now we're going to make 3 assumptions, which are the basic assumptions in renewal theory. The first assumption is a renewal equation. It says that Tn is a renewal sequence. So Tz is the identity minus Rz for all z less than 1, where Rz is an operator, is a power series of this form, and it converges absolutely. Okay, the sum of the operator norms converges. So this is just a generating function version of the renewal sequence, with the statement that the norms of Rn converge. In classical renewal theory, you assume that Rn are positive real numbers whose sum is 1. Then we are going to assume spectral gap. We are going to assume that R1, which is this operator, has spectral gap, and I want to assume, which I can always arrange by normalization, that the leading eigenvalue is equal to 1. With leading eigenvalue equal to 1. Okay? So the assumption is that 1 is a simple eigenvalue. The dimension of the eigenspace is equal to 1, and the rest of the spectrum is contained in a disk of radius strictly smaller than 1. And finally, I need an aperiodicity assumption, which again is a classical assumption in renewal theory. I don't want to be in a situation when when Rn is different from 0 only for n divisible by 5. That will mess me up. So I'm going to have to assume something to rule this out, and the right assumption to make is this. The identity minus R ei theta is invertible for all theta not equal to 2 pi k. That's the right form of the aperiodicity assumption. Okay, so now here is the version of the renewal theorem with rates of convergence, or at least one version of it. Actually, I want to introduce one more notation. So the eigenvalue is equal to 1, and I'm going to denote by P the eigenprojection. Okay, so in the spectral gap, we have a decomposition. The operator is equal to a projection P plus an error term N. So I want to call the projection term P, as I always do. Okay, so now here is the theorem. In the form that I'm presenting, it's due to Guezel. It's a generalization of a theorem of mine. And it says the following thing. Suppose P R prime 1, P is not 0, and the sum of Rk, k bigger than n, is big O of 1 over n beta, where beta is bigger than 1. So my theorem had beta bigger than 2. But in fact, beta bigger than 1 is there are important reasons to think about the case between 1 and 2. So it was an important improvement. So assume that this holds. Then we have the following asymptotic expansion for Tn. Tn equals 1 over A P. I will tell you what is A in a minute, plus 1 over A squared sigma L going from n plus 1 to infinity PL, and I will tell you what PL is in a minute, plus epsilon n, where, okay, P is the eigenprojection, I already told you. What is A? A solves the equation P R prime 1 P equals AP. Because of the spectral gap assumption, P is an operator whose image has dimension 1. So everything that you post-compose P to is going to be proportional to the same vector. So this always takes value in a vector space of dimension 1, and so does this, and it's the same space, so there is a proportionality constant. A is the proportionality constant. Okay? So I told you what is A. What is PL? PL is PL is sum I goes from L plus 1 to infinity. Is it L plus 1 or L? This is what I never remember. L plus 1, yeah. P R L P. And epsilon n, it's not a number, it's an operator. Is an operator which comes with a bound on the norm. It's little o, 1 over n to the beta minus 1. Okay, so how to read this thing? What this equation is telling you is that Tn, the element of the renewal sequence, converges to this limit at this rate. This is an operator, it's not a number, but it's a given operator. It's something that you can calculate, and we will calculate it in a minute. So basically it says that this is the limit. This is a good approximation on the level of operators of the distance from the limit. And this is an error term, which is operator valued, but the norm is tiny. Okay? So let me show you how this works in the dynamical context. And as I said, in the case of numbers, these are all classical results in renewal theory for numbers, due to Gelfond and Rogozhin and Borovkov and many people. This particular thing is, in the case of numbers, is a theorem of Gelfond. Not Gelfand, Gelfond, the number theorist. Okay, so let's see what happens in the dynamical context. So we induce on A, okay? We induce on a set A. So for example, think of a map which has a countable Markov partition, and you induce, and A is a partition, one of the elements of the Markov partition. So let's just calculate what all these things are. So Tn is 1A transfer operator to the power n f indicator of A. Rn, I'll remind you, is this times Tn f indicator of the return time equals n. Okay, phi a is the time it takes to return to A. And P, which is the eigen projection of the induced system, well, if we start with a probability preserving map, then what's the projection? It's the integral. So it's going to be the operator Pf is 1 over mu A, integral on A, f d mu. This is a number. We have to multiply it by the indicator of A because it's a function in L1 of A. Okay, this is the eigenprojection, not of the original transfer operator. It's the eigenprojection of the induced transfer, the transfer operator of the induced map. It's a map that lives on A, the set on which you induce. Okay, so now we know what is P. Now let's see what's A. Calculation of A. Okay, so let's just calculate P. Let's do it here. P R prime 1 P evaluated on a function f. Okay, and compare the result to PF. And the proportionality constant will be A. So this is 1 over mu A, integral of A. Now I'm applying this P. And I'm applying to it to this thing. Okay, what is R prime of 1? R of Z is some Z to the power n Rn. When you differentiate it, it's n Z n minus 1 Rn. Substitute Z equals 1, you get this sum. N Rn. Okay, so this is R prime 1. And evaluated at what? Evaluated at PF, which is 1 over mu A, integral of A, f d mu, times the indicator of A. Okay? So, what is Rn? We have a formula for Rn. It's the indicator of A, T hat n, all this times the indicator of phi A. So I can change this into this. Okay? This is a constant. It goes out. So we get 1 over mu A squared. Okay, one from here and one from here. Times the integral of A f d mu. It's this. Times the integral of n t hat n phi equals n d mu. I forgot about the indicator of the set because the image of this function will always be supported inside A. So I don't need to write it, but I hope we will not be confused by this. Okay, times integral d mu times, well, what's the result of the last integral? It's sum n goes from 1 to infinity, n mu phi equals n. So Katz's formula tells you that this is equal to 1. This is Katz's formula. So we get 1 over mu A times 1 over mu A integral f d mu, which is Pf. Okay, so A equals 1 over mu A. By the way, 1 over mu A is the expected return time to A. Different points will return to A after different times, and 1 over mu A is known to be the average return time to A. Okay, what else do we need? We need the PL. So let's see what's PL. The operators that give the rate of convergence. So PLF is sum L from n plus 1 to infinity PRLPF. So this is sum L goes from n to 1 to infinity 1 over mu A integral on A. This is P of RL. What's RL? RL is TL indicator of phi equals L. So that's RL. And now I have to substitute PF. PF is 1 over mu A integral F d mu. And I have to integrate like that. So you get 1 over mu A squared from here and here, integral f d mu times sum L going from n plus 1 to infinity mu phi equals L. So the result of this is, I'll just write it down. PL F is 1 over mu A squared, mu phi bigger than L, bigger than N, bigger than, this is Pn, bigger than N. Sorry, I apologize, I made it, this is Pn. L is the index, I flipped them, times the integral of f d mu on A, of course, everything times the indicator of A. Okay, so now we know all the terms in the expansion. And when you substitute, what do you get? Question? When you substitute, you get t hat n, the indicator of A times t hat n f of A is equal to 1 over A times this. 1 over A is mu A, so this 1 over A cancels this constant, and you get this number. That's not surprising. That's what should have been the answer. Then we get the term which measures the rate of convergence. You have 1 over A squared here. It exactly cancels out the 1 over mu A squared there. So you get 1 plus sum L goes from n plus 1 to infinity, mu phi bigger than L. And then you have epsilon nf. Now the point is that in dynamical situations, the norm, for example, if you apply this technique to the Manville-Poumot transformation, then the norm of this term is approximately the measure of this. So this thing here will be of order, let's say, 1 over, this is n to the power beta, so it will be 1 over n to the power beta minus 1. And this thing in norm will be little o of this. Okay? So it means that the transfer operator converges to this at this rate. This is negligible with respect to the rate of convergence. And the result of this is, so for example, for the Manville-Poumot transformation, or in fact for every map with Markov partition, if T has a Markov partition, and you use this formula for the transfer operator, you can get the estimate is asymptotic to, and really asymptotic to, 1 plus little o of 1, integral of f, integral of g, times L going from n plus 1 to infinity, mu of phi bigger than L. And it's really asymptotic equivalence. So when the method works well, you can get full asymptotic description of the transfer operator. Now, there is a defect in this theorem, as I stated it, which is the following one. I said that if you have this estimate, then you have this estimate, and the error term is little o of 1 over n beta minus 1. So this works perfectly well for the Manville-Poumot transformation, because for the Manville-Poumot transformation, the term which comes from here, the leading term, is indeed much bigger than this bound. But there are cases which have faster decay of correlations, which is not exponential. For example, there are situations when the rate of decay of correlation is a stretched exponential. That's still a case without spectral gap, because it's not exponential, it's only stretched exponential. And of course, it will be covered by this condition, because stretched exponential convergence is much faster than this. But when you apply the theorem to this case, suddenly you find that the error bound that you have dominates what should be the main term. So you don't get asymptotic equivalence. The error term is too big. So there are by now many developments of this theorem for faster rates of convergence. So most notably results by Guezel for probability preserving maps, and also by Ian Melbourne. And there are even results for infinite measure preserving transformations. for asymptotic behavior of the iterator of the transfer operator for infinite measure preserving transformations due to Melbourne and Terhesiu. Where what they do is they have a version of this theorem where you assume more on the tail of Rn, but you say more on the error term, so as to keep the result non-empty. Okay, so this is what I wanted to say, and I'm not going to bombard you with any more information. What I would like to do now is much more important. I would like to offer my thanks, deep thanks for Ali and Daniel and Benito and the other organizers for the wonderful work in organizing this conference. Organizing conference is a very, very difficult thing to do. I know it from experience. But what I find almost superhuman is to do it with a smile till the end and with patience and with kindness. And this is really, really admirable. And I would like to thank you very much on behalf of all of us.